Welcome to Chemistry at Hananiga High School. Today we'll be looking at our last set of notes dealing with molecule polarity and intermolecular forces from the chapter. First off, when we're looking at molecule polarity, you need to understand that bonds can be polar and so can molecules. So bonds can be polar and nonpolar, and so can molecules. Now, molecule polarity starts with bond type because if there isn't polarity within the bond, there's no way there's polarity within the molecule. And polarity, we're talking about basically the same kind of thing. In a bond, like in HCl, there's a bond. The chlorine is more electronegative than the hydrogen, so it shifts the electrons towards the chlorine, and this side ends up slightly negative, and this side ends up slightly positive. Remember, sigma positive, sigma negative. Well, that would be a polar bond type situation. Well, molecules can have that same thing happening. So is there a shift in electrons to a certain part of the molecule that would make that part of the molecule slightly negative and the other part of the molecule slightly positive? So molecule polarity really starts with bond polarity. The problem is when we've got a polar molecule. It would make sense that if there's no polarity in the bond, there's no polarity anywhere in the molecule. But when you have a polar molecule, you don't always, or a polar bond, you don't always get a polar molecule. And the reason is because of perfect symmetry. Now, if you remember in our discussion yesterday dealing with different types of molecule shapes. We classified some of them as symmetrical and some of them as non-symmetrical. And we talked about it as like tug of war symmetry. If we had two people pulling exactly opposite each other with the exact same force, they would cancel out. So when you're pulling exactly opposite and you're pulling with the exact same force, you're going to cancel each other. And that's what our symmetry is. So linear, trigonoplanar, tetrahedral, those were all shapes that can have symmetry. Now, perfect symmetry means they're all pulling with the exact same force, which means all of the outside atoms are the exact same type of element. So if you have one of our symmetrical shapes and all of the outside atoms are the same element, then you have what we call perfect symmetry. And your bond polarity is going to cancel out and you'll still get a nonpolar molecule. So to review, if you've got a nonpolar covalent bond, it doesn't matter with the symmetry, so don't even look at the shape. If it's nonpolar bonds, we automatically know it's going to be a nonpolar molecule. But when it's a polar covalent bond situation, then yes, we have to look at our shape. So we look at our Lewis electron dot and we see, does it have perfect symmetry or not? If it does have perfect symmetry, the bond polarity is going to cancel out and we'll still get a nonpolar molecule. The only way to get a polar molecule is if we have polar bonds anywhere in the molecule and we don't have perfect symmetry. In that case, we're going to end up with a polar molecule. So when you're doing these, a lot of times you're going to end up with non-polar molecules. And that's because I want you to practice it from many different angles. That doesn't really mean in the real world that more things are non-polar than polar. It just means that in the types of problems where we're practicing, different types of bonds, different types of shapes, you're going to end up seeing nonpolar molecules a number of different times. Now, once we know what the molecule type is, then we can look at how the molecules behave between each other. And that's known as an intermolecular force. A force of attraction between different types of molecules is what we call an intermolecular force. Now, we've got two different types of molecule, polar and nonpolar. And those different types of molecules are going to attract each other differently, simply because there's a difference when you have polarity within a molecule, when you have positive and negative regions, which we call a dipole, because we have two poles, slightly positive regions and slightly negative regions. So when you got a polar molecule, our most common type of force would be what we call a dipole-dipole attraction. The dipole in one molecule being attracted to the dipole in another. Now, a second ago, I looked at HCl, which as a molecule would be a polar molecule because it's slightly negative on one side, slightly positive on the other. Now, when we have another HCl molecule next to this one, with its slightly positive side oriented near the slightly negative side of the other one, we end up with an attraction occurring between these two. So it's not a bond, it's kind of a weak attraction between, we call an intermolecular force or an intermolecular bond. Not as strong as the bonds inside, like our covalent bond, but it is a force of attraction between the two that helps hold these things together. And remember, melting and boiling is separating apart particles. So if we have substances with a relatively strong attraction between, they're going to be hard to melt and they're going to be hard to boil. So chances are those types of things would be solids or liquids at room temperature. So the type of attraction in between affects how our molecule behaves in the real world. Boiling point, melting point, evaporation rate, solubility, tons of things can be affected by whether a molecule is polar or nonpolar. So polar molecules, and that's our key here. If we have a polar molecule, chances are the attraction between our polar molecules is an attraction between two dipoles. So the dipole in one attracting the dipole in the other, and that's why we call it a dipole-dipole attraction. Now, there's another way in which a polar molecule can have an intermolecular force, and it's really a super strong type of dipole-dipole. So our next type of intermolecular force we're going to look at is what's called hydrogen bonding. Notice it is still when we have polar molecules. So if I have a polar molecule, it's either a dipole-dipole or a hydrogen bonding intermolecular force. It's got to be one of the others. Now, hydrogen bonding is really a very strong dipole-dipole, and it involves a very specific situation that can come up when you have a molecule with a nitrogen, oxygen, or fluorine that has a hydrogen bonded to it. So if you have an NO or F with an unshared pair of electrons, so something like H2O, it's going to look like this. It's got two unshared pairs. If we have another H2O nearby this one, what we have is a super strong dipole-dipole situation. Now, the oxygen here in this substance is very strongly electronegative. So it's going to pull that electron it's sharing with hydrogen away from the hydrogen and towards the oxygen. So I'm going to end up with a very strong slightly negative region here because N, O, and F are in our upper right-hand part of the periodic table. They're our strongest electronegative substances on the table. So they do an excellent job of pulling that electron away from the hydrogen in the bond, and you end up with a very strong, slightly negative situation at the oxygen. Well, the same thing is happening here. This oxygen is pulling that electron away from the hydrogen. And remember, unlike everything else on the periodic table, hydrogen has no other inner level electrons. All it has is the one electron on its valence level. So when you pull that electron away, what you do is you expose the nucleus of the hydrogen. So literally, it's the nucleus of this hydrogen that is exposed to the outside world. And distance kills attractive forces. The farther away two oppositely charged things get, the weaker they hold on to each other. Well, as two oppositely charged particles get closer and closer and closer, the stronger they attract each other. That's actually something called Coulomb's law, which we get a lot into in second year chemistry. But for now, you just need to understand is we have an exposed nucleus, and that's going to get very, very close to that very negative oxygen, and it's going to form a super strong attraction we call hydrogen bonding because it always involves hydrogen. But be careful, it's not just hydrogen that we need. We have two parts to this. We need hydrogen stuck to an NO or F. So we have to have a hydrogen and we have to have that bonded to an NO or F with unshared pairs of electrons on it. So we get that super strong attraction that's negative from the electronegative NO or F, and we get that exposed nucleus from the hydrogen. And then we get what's called hydrogen bonding. And this is an incredibly important type of bonding. Most of our biomolecules, DNA, and many other things inside our body, hydrogen bonding plays an important role in how those things interact each other. The double helix in the DNA molecule itself, at the double helix where the two spirals come together, it's coming together through hydrogen bonding. So this is an incredibly important and very strong type of hydrogen bonding. So examples would be HF and H3, H2O. All of these have a hydrogen stuck to a very electronegative NO or F. So there's a memory aid you can use to remember this. When you have polar molecules, the type of intermolecular force will be dipole-dipole unless it's strong enough to be hydrogen bonding. Enough sounds like enough. So when you have H to an N over F, you get hydrogen bonding. And this is a super strong dipole-dipole. Now, the last type of intermolecular force is our London dispersion forces. And that's a very weak force of attraction between nonpolar molecules. So if you have nonpolar, it's automatically London dispersion forces. There's nothing else to choose from here. And technically, London dispersion forces are in all substances, but usually the dipole-dipole hydrogen bonding in our polar substance is much more important than the London forces that might exist. But it's the only type of force in a nonpolar molecule. Now, it's caused by a momentary dipole caused by the shifting of our constantly moving electrons. Now, the easiest way to see how this can happen is to draw a very simple molecule. So let's picture a molecule we're going to cut in half, and that molecule has 4 electrons in its electron cloud. Now, if it's nonpolar, we're going to get an equal distribution of electrons, and we'd expect most of the time to have 2 electrons on one side of the molecule and 2 electrons in the other, an even distribution of electrons. But remember, these electrons are constantly moving. So over time, as these things move around, this electron might, for a brief instant in time, end up over here. And then at that point, when that electron is shifted, what we have is a slightly negative region on this side, a slightly positive region on that side. We've created a dipole. But it's only going to exist for a very short period of time because sooner or later that electron is going to move back over here. So for a brief instance in time, we get momentary dipoles. Now, the bigger electron cloud is, the more likely this is to happen, the stronger that dipole is going to be and the longer it's going to exist. So with larger nonpolar molecules, this can actually become a pretty significant force. But really, when you have a nonpolar molecule, the only type of attractions you get between particles are these weak London force attractions caused by the movements of the electrons and the temporary dipoles that can get created. Now, we know if it's a nonpolar substance then that the type of attraction between them is going to be a relatively weak London force. So nonpolar substances aren't very strongly held together, so they're going to melt and even boil very easily at very low temperatures. So anything in the world around us, carbon dioxide, which we exhale, you know, is a gas, oxygen gas, 20% of the air around us, nitrogen gas, the other percent, 80% of the air that's around us, all those things are gases. All of those things are nonpolar molecules. The reason they're gases is they have very weak attractive forces, so they exist as gases in the world around us because they've already melted and they've already boiled. So intermolecular forces are an important part of understanding how a molecule is going to behave. And that ends our last set of notes over Chapter 8, covalent bonding.